All right, question number 4. We've got a container. It's got 20 grams of neon and 8 grams of helium. One thing we need to really review, when they talk about the mass number, that means the number of grams in a mole. So let's be really careful. So I've got 20 grams of neon and there's 20 grams in a mole. So to get the number of moles of neon, that's going to be 20 divided by the 20, and that's 1 mole. And to get the moles of helium, I'm going to take 8 grams of helium divided by the 4 grams needed to make up a mole, and that's going to give me 2 moles. And you know what? I should be a little bit more careful. That's He here for helium, and Ne here for neon. So if I want the ratio of atoms of neon to atoms of helium, that's going to be this 1 mole divided by 2 moles. And that's how I'm getting 0.5. All right, question number 5. A substance changes from solid to liquid at its normal melting temperature. And we want to know what change occurs in the average kinetic energy and the average potential energy of its molecule. So let's be really clear. Whenever the temperature, first, let's go back to the IB definition of temperature. Temperature is a measure of the average kinetic energy of the particles in a substance. And so when temperature goes up, average kinetic energy goes up. Okay, and that's good for us to know. So using that fact, a substance changes from solid to liquid at its normal melting temperature. What change, if any, occurs in the average kinetic energy and the average potential energy of its molecules? Well, when we're going from solid to liquid, let's remember the equation that governs that is Q equals mL, and that implies there is no temperature change happening at all. So if there's no temperature change, that means there's no change in average kinetic energy. So right away, that actually eliminates choice B and C as possibilities because they claim the average kinetic energy is increasing. That can't possibly happen. So what does change when something changes from solid to liquid? Well, what actually ends up happening is there are sort of attractive forces among the particles, a kind of potential energy, a kind of intermolecular potential energy among the particles. And when heat is added and it melts, that average potential energy increases as the particles move further from one another. So that means something is changing, and it's actually the average potential energy. So the other thing I want to say is that during a phase change, that reads badly. So during a phase change, potential energy changes. We don't mean some weird gravity thing. We mean the intermolecular potential energy between the molecules. And then for these two boxes here, first of all, we get two identical boxes with an ideal gas. And I'm just going to glance at all the variables. So I notice N, I notice T, I notice P. Okay. Ideal gas and these letters suggest to me that this is going to be some kind of a Pivnert ideal gas problem. So here's the idea. Let's write down an equation for box X, an equation for box Y, and do the math that they ask. So I know that Px equals, Px times the volume of the box that it's in equals N R T. And then for box Y, we have Py times V equals 2n times r times t over 3. And now what we're going to do is we're going to divide these two equations to get the ratio of px to py. So I'll say pxv, whoops, pxv divided by pyv equals nRT divided by, and I take the right side of this one, 2n RT over 3, like that. Let's cancel what we can cancel. The V's cancel, the N's cancel, the R's cancel. Now the rule for this is when I divide T by T over 3, this 3 actually goes on top. And that's the rule. So this ends up becoming that Px over Py equals 3 over 2. And that's how we get choice B. Lastly, the temperature of an ideal gas is reduced, which actually happens. So one thing we want to be clear on is that time of contact is always effectively 0. It's a very, very small number, and that contact time doesn't increase or decrease. It's just not something we think about in the ideal gas model. Now, we know that temperature correlates with average kinetic energy. So here's the thing. If the molecules have a smaller average kinetic energy, if the temperature, correlates with average kinetic energy, and you reduce the temperature, you're reducing the average kinetic energy. That means that they're moving slower, so they're going to collide with the edges of the container less frequently. That's the whole point of connecting temperature with kinetic energy and applying it to other problems. So that is page 2, and we'll move on to page 3 in the next video.